Now let's discuss specific steps for geometric corrections. Okay, so the first step, I personally consider this as the most important step, is called locating GCPs. So a GCP or ground control point is a location on the surface of the Earth that can be identified on the imagery and located accurately on a map. So, according to this concept, GCP is something very arbitrary and subjective. The selecting of GCPs all depends on the user of the map or the GIS analyst or remote sensing analyst. So it's skillful and it requires experience. You need to find something that can be easily identified in your reference map and also easily identified on your remote sensing image. For example, a very famous, very huge building, say a landmark, can be used as a very good GCP because it's not a random normal building. Maybe it's huge, it has special shape, so it can be easily identified on your reference map and also on your image. But on the other hand, a regular random residential house is a very bad GCP point, right? In a residential area, there could be dozens of houses. Okay, how can you identify the same house on your reference map and identify exactly the same one on your remote sensing imagery? So it's a pretty bad example to just choose a building that cannot be identified. And another example would be a cross of roads, right? So it's or in, say intersection of two roads. And if it is a big one, it's even better. So it's easy to identify it. Okay, so that's a principle. So the image analyst must be able to obtain two distinct sets of coordinates associated with each GCP. Okay, so image coordinates are specified in a row number and column number, and also map coordinates. Okay, in general, latitude and longitude. Okay, so like I said, you need to be very experienced to find out very good GCPs, but do not consider this as a very hard job. In this class lab, you will try to do that. Later, I will tell you how to do that. I will show you bad examples for GCPs and good examples. Okay. Okay, and obtain accurate GCP map coordinates using hard copy planimetric maps. You can also use digital planimetric maps, digital orthophotos, or GPS instruments. So today, hard copy maps are not very usually used. Usually, today when we're using remote sensing software such as ENVI, such as ERDAS, we need to find a digital reference map. And of course, this map should cover the area that is covered by your remote sensing image, right? So here is an example on the left side. It's just a regular map showing, I'm not sure Manhattan, but yeah, anyway, it's an island. It's an island. On the right side is the remote sensing for the same area. So on the left side, we have three GCP points. They are part of the whole GCP sets. So because one is called GCP 13, another one is 16, another one is 14. So these 3 points, these 3 GCPs, they are good examples. Why? Because they are all on the boundary between this island and the water body. So this boundary is relatively easy to recognize, to identify, right? Especially in remote sensing image. Because water is usually in dark color in remote sensing image, so this boundary can be easily identified. And let's say what other factors you need to be careful with. So all these 3 points, they are also identified in specific areas. For example, 14 and 16, they are both what? On a specific bay or harbor of this island. Here is a harbor. Here 16 is another harbor. So if you have prior knowledge of this area, say you are living there or you're very familiar with this area, it's not possible for you to select them wrong. And actually, even if you are not very familiar with this area, I mean, this harbor, the shape of the harbor here is very special in your reference map, and it can be easily identified here and here. Okay, and also this GCP point 13. This is what? The turning point of this boundary between the island and the water body. It is actually the very end of this island, right? So again, it can be easily identified in your remote sensing image. It's right here. So these 3 points, your prior knowledge and their special locations on this map and on this image makes sure that you cannot pick them wrong in both maps. Okay, so when you try to find GCP points, take advantage of your prior knowledge on this specific area and take advantage of different, say, different visual variables. See that, right? Shapes, right? Texture, right? And anything you can use to make sure that your GCP points can be accurately identified in your reference map and also accurately identified in your remote sensing image. So that's the purpose. Okay, so here we have more examples. Okay, so control points using image-to-image registration. So here we do not have a reference map. So a specific image, okay, or images, they are serving as reference map. So on the left side, we have reference images, okay, for this specific area. And this is the area, this is the area, okay? Okay, so for figure A, here we have what? We have a pair of images, right? On the left side is the reference one. On the right side is the one to be referenced. So we have how many GCPs here? I think 15, right? 15. So here is a result of GCP points finding. Here, this pair is another result for another try for GCP selecting. The top one is a good example. The bottom pair is a bad example. Why? Here, for the good example, you can see that the analyst tried to distribute all GCP points across the whole image. They are spreading out. They're spreading out across the map, across the image. On the other hand, this bad example, from them, you can see that all these GCP points, they are relatively clustering, or you can say they are only covering a part of the image, right? This part. But how about this part? Here, right? How about here? So when you are using this bad set of GCPs to do geometric correction, the result is that your correction is performing well across this area covered by GCP points. But this correction will be pretty bad for those areas not covered by GCPs. So what I'm trying to say here is that when you find GCPs, you want to make sure there are at least a dozen of them. Okay, the more the better, but not too many. Okay, I think 2 dozens would be good enough if you do not require very accurate geometric correction. I mean, it depends. Okay, there is no specific good answer or bad answer, correct answer or wrong answer for the number of GCPs, but at least try 15, 16. Okay, and spread them out. Make sure that they are actually generally covering the whole image. Do not pick GCP points only from a part of your image. Okay, so that's another, say, tip. Okay, another trick for selecting GCPs. So first principle, try to find some locations that can be accurately and easily identified in reference image or reference map and your image to be referenced. Secondly, try to distribute your GCP points across the map. Okay, do not just choose GCP points from a part of your image. Okay. Okay, now step 2. After selecting GCPs, we need to do something called geometric transformation. This is based on the establishment of the relationship, mathematical relationship between reference map locations and the remote sensing image locations. When I'm talking about locations, they're actually locations of GCPs. Okay, your software will use the location of GCPs on your reference map and the locations of your GCPs on your remote sensing image to try to establish this mathematical relationship using polynomials. Okay, using polynomials. And after that, as the relationship is established, the computer will do the geometric transformation to change the locations of original pixels. So the first logic or first magic for the first method here for geometric transformation is called the logic of filling a rectified output matrix with values from an unrectified input image matrix using input to output or forward mapping logic. Okay, so the first thing I want to explain here is matrix or matrix. You can consider a matrix a bunch of values. Okay, and each value has a specific row number and a specific column number. So a remote sensing image is formed by what? Is formed by a bunch of pixels, and each pixel has a specific value, right? So a remote sensing image is actually a matrix in your computer, right? Because each pixel has a value, and each pixel has a row number and the column number. So when we're talking about matrix, okay, that's actually the real identity of an image. An image is a matrix to your PC, to your computer, okay? So the forward mapping logic is that this is an unrectified image, right? For example, this specific pixel here has a column number of 2 and a row number of 3. Its value is 15, okay? According to that polynomial, this should be polynomial sets, right? Because you have to calculate the x value and the y value for rectified image, right? So what's the actual x value and y value of this pixel in the rectified image? This equation set is trying to answer that question. So x prime and y prime, they are locations in the original input image. X and y, they are locations in the rectified output image. Okay, so this pixel was here in the unrectified image, and it should be here in the rectified image. You may have noticed that the new coordinate is 5, 3.5. 3.5 is not an integer. So it's somewhere between 3, 5, and 4, 5. Okay, so this is an issue because you cannot use a non-integer to address the location of a pixel. So you need to use something called resampling to make sure that the new pixel's value is distributed to other new pixels in these rectified images. Okay, so 15 should not be here. Should not be here either. It's somewhere between these two pixels. So how to distribute this value 15 to other two pixels in the output image? Like I said, you can use something called resampling, and the easiest way is called nearest neighbor. Or you can use other spatial interpolation method to do that. But in this class, for now, you don't have to know that. So this is a forward mapping logic from input to output. Another method is called output to input or inverse mapping logic. Okay, it means that, okay, we need to look at the output image first and find a specific pixel. For example, in the output pixel, this pixel is at location what? 5, 4, right? 5 is for column number, 4 is for row number. So this time, we just select this pixel first. And we need to go back to the input image to find the value for this pixel. Okay, okay. So this time, integer coordinates are assigned to a specific what? Pixel in the input image. That pixel actually doesn't exist, right? Because only integers can be assigned to pixels, but this pixel should be 2.4 and 2.7. It doesn't make sense. So how to find a value for this pixel so it can be assigned to this output image? Okay, again, we can use something called resampling. Okay, and the easiest way of doing resampling is called nearest neighbor. So this is the pixel you want, right? It doesn't exist in the input image, but we can do compromise. We can find the nearest existing pixel, right? Who is the nearest neighbor of this pixel that does not exist? It's this pixel, right? It's the nearest neighbor to this not existing pixel. So its value is 15. Okay, I will just take that. Okay, I will just assign the value of this pixel's nearest neighbor to that pixel you want in the output image. But this is just an inverse logic, inverse method of this forward mapping logic. So in the forward mapping logic, we identify a pixel in the input image and try to find its location in the output image, and we deal with the pixel value. Here, we satisfy output image first. Okay, for this specific output image pixel, according to this mathematical relationship between reference map and remote sensing image, where it should be in the input image, it should be here. Okay, it's 2.4, 2.7. It does not exist in the input image. Fine, let's just find its nearest neighbor that exists. Okay, so this is the nearest neighbor and its value is 15. Okay, I'll just take that. Okay, assign 15 to that pixel in output image. So output to input inverse mapping logic is the preferred methodology because it results in a rectified output matrix or image with values at every pixel location. Okay, so usually it is recommended to use this method because it's convenient. We don't have to do anything on output image pixels because each pixel should have a value from input image, and you do resampling in input image. Okay, but if you are using forward mapping logic, you could say that a specific pixel in output image may not have a direct value because according to this method, uh, 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 this pixel here has a pair of coordinates with non-integers, and this pixel is projected from your input image. So usually we use this inverse mapping logic. Okay, so the models. Let's talk a little bit about polynomials. We have linear and nonlinear ones. They have their pros and cons. I'll just introduce them here. Okay, we're not going to go deep about how to create them. Okay, so usually we use x and y for ground coordinates, map coordinates, or coordinates of rectified image. Okay, or we can say coordinates for output image. So x prime and y prime, on the other hand, they're image coordinates of input image, or you can consider them as coordinates before geometric correction. So we can use first order polynomial or linear transformation. Okay, so x prime and y prime, their relationship can be addressed here. So usually we put x, y here as the result. As the results, say that for this equation set. But similarly, we can use x prime and y prime as outputs, as long as this equation set is established. Okay, so we can also use second order polynomial or nonlinear transformation. So you can say there are squares. We can even use third order or even higher order polynomial or equation sets to do the same thing. So you would say, which one should I use? First order, second order, third order, or even higher order? Let's talk about first order first. I mean, linear transformation is pretty simple, right? So x predict is equal to a specific offset plus a coefficient multiply x plus another coefficient multiply y. Okay, if this is the situation, the offset is 0, x predict is equal to actually x. A y predict is actually equal to y. So there is no transformation. Input, output, they are the same because the coefficient here for x is 1. The coefficient here for y is 1. Okay, and another coefficient is 0 and 0, and there is no offset. So actually, x predict is equal to original x. Y predict is equal to original y. So there is no change here. Of course, you can add an offset. Okay, as a result, the relative spatial relationship among these pixels did not change, but this whole matrix has been moved from its original location to another location thanks to this offset. 1 unit offset along x and 1 unit offset along y. So this is the result. Of course, we have other examples here. For example, there is no offset here, but you can change the coefficient from 1 to 2, which means that in the output image, x value will be 2 times of the original x value. Similarly for y. So this is the result. You can say all these pixels, they are distributed in a broader space, in a larger space. Okay, of course, you can change coefficients arbitrarily, right? But these are just examples of first order transformation. This is what it does. And for second order, for third order, even high order, it's relatively hard to address them using simple figures. Okay, so I'm just showing you the first order transformation so you get a general impression about what these equation sets do to your image, So let's get back to that question. Which one should I use? First order, second order, or even higher order? So here is some comparisons. So here, we're not talking about remote sensing image, okay? I'm using this curve to address the difference among different polynomial equation sets with different orders, okay? So this is the curve we want to simulate or we want to fit using polynomials. This is observation. Or you can say all these points, they are observations. They are connected by this curve. So yeah, you can just consider this curve as your observation or all those points connected by this curve as observations. It doesn't matter. So this is the result of linear transformation or linear fitting. So again, this curve is the observation. And since you are using linear regression or linear fitting, you are trying to use this straight line to match this curve. It's so obvious, right? It doesn't fit, but it's easy enough. It's just y is equal to b plus ax. So it's not accurate, but it's so easy to calculate, which means less computational burden. It's fast, but not accurate. So now let's use something more complex to match this observation. This time we use second order polynomial. So again, this is the observation, right? This curve is still here. When we're using second order polynomial, we also have a curve trying to fit this observation curve. So it's much better than the linear fitting. It's much better than straight line. But still, there is what? There is error. There is error. Okay, it's better, but obviously this polynomial is it is not much complex, much more complex. It's just more complex than the linear one, right? Okay, so you can just increase the order again using a third order polynomial to fit the observed curve again. So here is the result. So you can see this curve here addressed by this third order polynomial is very close to the observed curve. So if you compare the first, image B, figure B, figure C, and figure D, which one is the best fitting of the observed curve? Obviously, figure D, right? But there is sacrifice. If you are using a computer to do the fitting, it will be much slower using this third order polynomial than the first order polynomial. So you want it more accurate, sure, but you're going to use a more complex, much more complex polynomial here to finish your job. So it's the same thing when we're talking about geometric transformation. Okay, you can simply use very simple first order polynomial to address the relationship of coordinates on your reference map and your remote sensing image. Sure, it's easy, but not very accurate. You can use second order or third order polynomial to do the same thing, to address the same relationship. It will be more accurate, but computational burden is much higher than linear transformation. Okay, so there is always compromise. Okay, there is no perfect method for this geometric transformation. Okay, okay, here is an example. It's NASA Atlas near-infrared image of Lake Murray, South Carolina, obtained on October 7, 1997, at a spatial resolution of 2 meter by 2 meter. It's very high, not extremely high, but very high spatial resolution. So here is the rectified image. Okay, you can say it's actually the shape of this image is not a regular, is not a rectangle. It's actually a curve, right? It's an arc that fits actually the shape of satellite orbit. It should be a curve instead of a straight line. Okay, so that's the reason why when you rectify some image, before the rectification, the image is a square or is a rectangle, and after rectification, it's a curve. It has a shape of a curve. So it's a curved image. Okay, so the image was rectified using a second order polynomial. Usually second order is good enough, okay, to adjust for the significant geometric distortion in the original data set caused by the aircraft drifting off course during data collection. Unfortunately, I don't have the original image here. It would be better if you can compare, but right here, it's the result. It's the result. Okay. Okay. Third step is about image resampling. I mentioned it a little bit, right? Nearest neighbor resampling is the simplest one. Of course, we can use bilinear interpolation, okay, or even higher order resampling method, cubic convolution. Okay, the data file values of the 4 closest pixels. Linear interpolation technique. Image is smooth. Some extremes of data file values are lost. Okay, it means that when you need to find the value of a specific pixel, you find its 4 closest neighboring pixels and use linear interpolation to find out the value of the target pixel based on its 4 closest pixels. Of course, you need to know the values of these 4 neighbors and use specific mathematical method to find out a value for the target pixel based on its neighbors. Okay. The data file values of a set of 16 pixels. This means that how can I say, more neighbors are employed to calculate the value of the target pixel, okay, compared to bilinear. For bilinear interpolation, 4 closest pixels, okay, so more pixels are introduced here in cubic convolution, okay. For details of this resampling methods, I will introduce them in the next video. I will stop here for this video. Okay, thank you.